So, hello everyone. Today we're going to talk about the topic Gauss divergence theorem. So this is a physics topic, by the way, but the concept used in this theorem is related to the vectors, which belongs to the subject math. So we're going to talk about how the vector operation, which is divergence of a vector, is applied in this theorem. So let's move on. So let's start. Actually. What is first of all, what is divergence? That the divergence of a vector field measures the density of change in the strength of the vector field. So the field lines diverging uh, in simple terms. That's what we say as divergence. So in this diagram, this is not divergent basically. This is convergent. So convergence is the opposite of divergence. Therefore, divergence is represented as less than zero. Here, the field lines are diverging from this specific charge point. So this is greater than zero. Here, this is not the field lines are not diverging from the point, but they are in different directions. So it's not related to this specific point. Therefore, the divergence is equal to zero. So mathematically, divergence of a vector is represented by this equation, which is lambda dot vector field. So divergence and divergence we use dot product. So basically, dot product is a vector, a scalar, and a vector, and or a vector and a vector. So when you multiply two magnitudes, the result is a scalar product. So the divergence of a vector is a scalar product. So let's go through the divergence theorem statement once. The Gauss divergence theorem states that the vector's outward flux through a closed surface is equal to the volume integral of the divergence over the area within the surface. So just go through the statement once again. If you cannot understand, we'll go through the formula that the statement defines, so that makes things easier. So we'll go through the formula. So this is what the statement says. The integral of the divergence of the surface of the enclosed surface. So this symbol represents the enclosed surface. Sorry. So this symbol represents the enclosed surface is equal to the volume integral of divergence. So we see that this is the phi. This symbol is called as phi in mathematics. So phi dot divergence of the vector. So sorry, phi dot flux of the density flux of the field or of the Gaussian surface, because enclosed surface is also Gaussian surface. So basically, Gaussian surface is the surface we use while defining Gauss divergence theorem. So phi dot density vector, this is equal, that is the divergence of density of the flux. So volume integral of this divergence is equal to the enclosed surface integral of the dense. This is the outward flux. So outward flux within the closed surface. So we can go through the proof once. So consider a volume V enclosed by a Gaussian surface S. Let a charge dq be enclosed by a small volume V. So we're considering a small part of the Gaussian surface. So if we consider a small elemental part of the Gaussian surface, we can give it the density as q by v. But since we are referring the small elemental surface, we take it as dq by dv, and by this we get dq is equal to rho v dot dv. So the total charge enclosed by the Gaussian surface is equal to dq. So applying integral on both sides, we get q is equal to enclosed volume integral dq, which is equal to enclosed rho v dv. Whole integral of rho v dv. So, but from Gauss divergence theorem, we know that rho dot d vector is equal to rho v. So the divergence of d vector is equal to rho v. So basically, this is what we refer as divergence in mathematics. So Q is equal to closed volume integral of psi dot phi dot d vector dv. But according to Gauss law of electrostatics, so the other formula for Q is closed surface integral of d dot ds. So from these two equations, we get this final formula, which is the Gauss divergence theorem. So basically, this is the scalar product, and this that we use over here is the divergence of the vector d. So this is how we use divergence of vector in physics on the topic of the Gauss divergence theorem. So that's it for today. Thank you.